Okay, so in the last session, we talked about Dijkstra's algorithm, and I got a bunch of emails questioning me about the reason why this algorithm is correct. So I'm just going to go over the correctness proof one more time. So this is what we're going to do. We're going to have some starting vertex. And remember that I have a weighted graph, so every edge has a weight now. And let's say that my starting vertex is vertex number 2, right? And then I said that I will have an array or maybe some other data structure that basically tells me what is the best distance that I have found to each of the vertices until now. So it's like my estimate of the distances. So I have my vertices and I have the distance to them. And here my starting vertex is vertex 2. So I want to find the distances from vertex 2. So initially I would say that the distance to vertex 2 is 0. And I'm assuming that the distance to every other vertex at this point is infinity. I don't know anything about the distances to the other vertices. Okay. Now, the idea was that every time I'm going to take the vertex with the smallest distance, and I'm going to say, I'm sure the distance to this one is not changing, and I'm finalizing it. So in the first step, it's trivial that this is correct, right? So the distance to vertex 2 is 0, and I cannot get a distance of smaller than 0, because I said that all of my weights are non-negative. We don't have like negative weights and negative cycles and any of that. So if I'm starting at vertex 2, I can definitely finalize vertex 2 and say that the distance to vertex 2 is 0. Now, when I finalize a vertex, I also update the distances to all of its neighbors. So now I know that the distance to vertex 1 is at most 1. I know that the distance to vertex 4 is at most 0, and the distance to vertex 5 is at most 1. Okay. Now, at this point, again, the argument is very similar to before. I'm just going to say, among these distances, 4 has the smallest distance. So if I'm starting a path from vertex 2, I'm going to take one of the edges out of vertex 2, right? And I know that if I take this edge, I will reach 4 with a cost of 0. But if I take any of the other edges, I have already exceeded the cost of 0. So it's impossible to reach 4 with a cost of less than 0. So I can say that the distance to 4 is finalized. Okay, so I finalize 4. Let's say this means it's finalized. And I update the distances to all of the neighbors. So now the distance to 2 should be updated, but it's already finalized, so I don't care about that. The distance to 3 becomes 0 at most. And the distance to 5 becomes at most 3, but it was already at most 1, so I don't need to update it. Now, again, I'm going to do the same thing. I have a bunch of vertices that I've shown in red here, and these are my finalized vertices. Now, here's the argument in its general form. If I start at this starting vertex, which is already finalized, and if I want to reach some of the unfinalized vertices, at some point I have to exit the set of finalized vertices, right? So that's the point that I want to really focus on. So here I'm going to say that among the unfinalized vertices, the smallest distance is to 3. So it means that I have a path that starting vertex 2, and it gets here with a cost of 0 in this case, right? Now, any other path that goes outside of the red vertices is going to have a cost of more than 0, right? Because I have all of those costs as distances here. So it's impossible that I can find a different path that gets to this vertex 3 and has a cost of less than 0. So I can take the vertex that has the smallest cost, and I can say the distance or the cost to that vertex is already finalized. And then it's the same argument over and over again. Now I update the distances. So the distance to 1 becomes at most 2, but it was also already 1. And now again, I find the smallest distance. In this case, I find 1. And I just continue like that. So that's the reason why Dijkstra works. And we talked about how to code it. If you haven't seen that, it's already on Canvas. And we talked about the runtime. So today we're going to talk about a completely different problem. Okay, so today's topic is disjoint sets with union. And the problem that I want to solve can be represented in two different ways. I'm going to give you both formalizations of the problem. They're actually the same problem. So in the first formalization, I have a graph, and initially my graph just has a bunch of vertices but doesn't have any edges. And then I have to answer a bunch of queries. I have to do a bunch of operations. And the operations either tell me to add an edge to my graph or ask me if two specific vertices are in the same connected components. Okay, so this is what I have in my input. I have, first I have an empty graph with n vertices, so I just give you n. And then let's say I also ask you to perform m operations. Now, each operation is one of these two. It's either asking for me to add an edge between u and v, so it literally just adds this edge to the graph, or it asks me a question. It says query uv, and I have to say whether u and v are in the same connected component. And this is an undirected graph. So the question is there a path from u to v? So this is my output. For each query, I should output 1 or yes if u and v are in the same connected components. Okay, so it's a pretty easy situation, right? I start with a bunch of vertices. I already know how many vertices I have at the beginning. And every time, let's say I also number them 1, 2, 3, 4, 5, 6. And I should either add some edges. So maybe I say add the edge 2, 4. Then I should just add this edge. And then maybe I do a query. Maybe I ask 1 and 5, are they in the same connected component? And the answer should be no. And then maybe I connect 2 and 5. So I say add 2, 5. And then maybe I connect 1 and 6. And then maybe I connect 6 and 5. And now I might do a query. I might ask, for example, are 1 and 4, and by the way, I sometimes write Q, sometimes write query. I ask 1 and 4, are they in the same connected component? You should say yes. I ask 2 and 5, are they in the same connected component? Yes. And so on. So that's the problem. Now, of course, we can have a very simple solution to this, and the simple solution is keep the graph, right? Just have this graph as an adjacency list, and whenever you want to add an edge, you just add the edge to your graph. Whenever there is a query, you're asking whether I can go from vertex u to vertex v, just do a DFS from vertex u, see if you reach vertex v, right? So that's the obvious solution that comes to mind. And of course, instead of DFS, you can also do BFS. It doesn't really matter. So I can have a solution basically using DFS or BFS. But how much time does it take? So every add is going to take constant time now, every time that I'm adding an edge, right? because when I'm adding an edge from U to V, I'm just changing the adjacency list of U and the adjacency list of V. I'm just adding one element in each of them. It's a vector, addition is O1. But now every time that I'm doing a query, that's actually taking On plus M, where N is the number of vertices and M is the number of edges that were added before this query, right? Because I'm doing a DFS. Now, of course, this is fine if you want to do just one query, but I want to consider a case where I'm doing tons of operations. So let's say my M is really large. Again, I'm saying I'm doing M operations. I have N vertices. So if every query takes this much time, my total runtime is Mn plus M squared. And I'm not happy about that because I have M queries. It's just M times this. Okay. So I want to do it faster. Now, to do it faster, I'm going to look at this problem as kind of a different formulation, but you will see that the two formulations are obviously the same. So here's the other formulation. I can say my input initially consists of N elements, and each element is in its own group or its own set. Okay, so I have, let's say, N sets. I have a set that has only element 1, I have a set that has only element 2, so on, and I have a set that has only element 10. And I want to perform M operations again. And my operations are as follows. I have one operation which is called merge, and I give you two numbers, I and J. And what this means is take the set that contains I and the set that contains J and merge them into one set. Okay, so merge the sets that contain I and J. Now, of course, it's possible that I and J are already in the same set. In that case, the merge doesn't really do anything. It's like the same set remains there. And then I also have a query which gives me two vertices I and J, or two numbers I and J. And you should tell me whether I and J are in the same set. Okay, so I have two operations. I can merge my sets or I can query. And again, my output is for every query, basically decide whether I and J are in the same set. Of course, at the time of the query. Now, why is this the same as the previous problem? Because, well, our sets are just our connected components, right? So you can just think of these numbers 1 to n as the vertices of this graph, right? And when I say merge I and J, it's like adding an edge between vertex I and vertex J. And that would merge the connected components of vertices I and J, right? And when I do query IJ, I'm asking, are they in the same set? It's the same as the query that I had here, which was, are they in the same connected components? So the two problems are the same. So I can just use the same algorithm as before, of course. But again, the whole point of this was that I don't want to do that. Now, what's the problem with this algorithm? The problem with this algorithm is that I have way too many edges, right? So if I'm adding edges, at this point, it's just like a tree on this side, but maybe I keep adding edges that don't really matter. Maybe I add, for example, an edge from 1 to 5, but 1 and 5 were already in the same connected component, right? So adding this edge didn't really contribute anything. It did not change my connected components, but it's going to increase the time of my DFS or BFS because I'm going over all of the edges whenever I'm doing that. Right? So the first thing we can do is, before adding every edge, we can just do a query and we can ask, are these two endpoints in the same connected components? We can just do a DFS. And if they're already in the same connected component, don't add the edge. Right? Now, this ensures that you will always keep a forest instead of a tree. But the forest that you keep will have the same connected components as a forest instead of a general graph. But the forest that you keep will have the same connected components as if you've saved the whole graph. But then this one would basically increase the runtime of add edge, because every time I'm adding an edge, I'm also doing a query before. But now when I'm doing the query, I know that the number of edges is at most n-1, right? Because I have a forest, and like a forest is a bunch of trees, and a tree on n vertices has at most n-1 edges. Okay, so this basically reduces my query time to O(n). It will not have m anymore, but it also increases my add edge time to O(n). So my total runtime will become n squared, or actually no, m times n, because I had m queries, right? M operations. So m times n might be better than the previous one, which had like m times n plus m, but it's not a big improvement. We want much better improvements. Okay. So here's the idea. Let's say that for each one of the connected components, or each one of my sets, I'm going to just choose a representative. I'm going to use one of the vertices or one of the nodes in that set as the representative of the whole set. Okay, so for example, let's say that here I say that node 5 is the representative. And then in front of every node, I'm going to write the name of its representative. So this one is represented by 5. This one is represented by 5, 5, 5, 5. And let's add some more vertices here. So let's say I have 7 and 8. And let's say these were also all connected. And let's say that they were each represented by vertex 3. Okay. So if I have this kind of thing, whenever someone asks me a query, whenever someone asks me, are these two vertices in the same set or in the same connected component or not? That's basically asking, do they have the same representative? So I can answer the queries in constant time. I can just check, do they have the same representative? If yes, return true. If no, return false. Now, what happens when I want to add an edge? Or in this case, when I want to merge ing? Well, first, I do a query, because now queries are free. Queries are basically constant time. And I check. If they're in the same set, I don't have to do anything. There is nothing to merge. But if they're in different sets, for example, let's say I'm adding this edge. I'm adding the edge from 7 to 4. And they have different representatives. So they're in different sets. So now these two sets that had these two representatives have to be merged with each other. So they all have to have the same representative. So I will just pick one of these representatives and make sure everyone follows that. So let's say 3 becomes the representative of all of these vertices. So I change the representatives from 5 to 3. Some of you are laughing. Yeah, I know this is not optimal. That's the whole point of this session. Okay. So that's the idea. And right now it's a simple idea. Let's code it. And we will see that it actually gets better. So DSU with representatives. This is what I'm going to do. So let's say I just read some number n. And let's say I also read some number m. And then I have to do m operations. And every time I have to either do merge or query. So I show that with m and q. So I will just have one character, I read it. If this character is m, it's a merge. Otherwise, if it's a q, it's a query. Okay. And in any case, I have two vertices or two items. We can call them UV or we can call them IJ. Again, I just go back and forth between the two formulations of the problem. So let's say I have U and V, I read U and V. And if it's a merge, well, I just merge U and V. I will write it later. Otherwise, I just write the result of the query on U and V. Okay. Now I want to have representatives for all of the vertices. So here's what I'm going to do. I'm going to say, let's say I have a representative for every vertex. And let's say my maximum n here is something like this. So rep I is the representative of vertex I. Okay. Now, initially, every vertex is in its own connected components. Every set has a size of 1. So everyone is their own representative. So initially, I would say for every I from 1 to n, the representative of I is I. That's my initialization. Now, I want to do merge and query. Query is easier. So let's write query first. I have two vertices U and V. I want to see if they're in the same connected component. Or I have two elements U and V. I want to see if they're in the same set. And basically, I just have to check if they have the same representative. So I just return whether the representative of U is equal to the representative of V. And query is 1. Okay. Now I have merge. So I want to merge the connected components or the set that contains U and the set that contains V. Now, I first do a query. I say, if they're in the same set, return. Don't do anything. Okay, they're already in the same set. I don't care. Otherwise, take one of the representatives. So, for example, take the representative of U and also take the representative of V and just go over the whole array. And whenever you see one of them, replace it by the other one. So I'm just going to say for every I from 1 to n, I just realized my n is not global. So let me put my n here. For every I from 1 to n, if the representative of vertex I was RU, I just say the representative of vertex I becomes RV. Okay, so now all of the vertices that were represented by either R2 or RV are represented by RV. So the two sets are merged. Okay, what's our runtime? So this was, let's say, I'm going to call it the basic representatives algorithm. How much time do I need for my query here? That's constant, right? Because my query is just checking whether the two representatives are the same. But how much time do I need for my merge? That's actually O(n). Because in my merge, in the worst case, I have to go over all of the elements and I have this for loop and it takes O(n) time. Okay, so let me see if this works. Oh, I called it rep and then I wrote R. Sometimes I write rep, sometimes I write R. Okay, let's just use R. So, because I'm using it here. Okay. Let's run this. Let's say I have 8 vertices and whatever, 100 queries. And I'm just going to do, what did I call them? I called it M and Q, right? So I'm going to add 2, 4. I'm going to query 1, 5. It says no. I'm going to add 2, 5, add 1, 6. I'm doing this at 6.5, query 1.4, yes, query 2.5, yes, it seems it's working. Okay, so now we have this algorithm, but again, my runtime is not great because remember I have m queries and I don't have any control over them, they're part of my input. So in the worst case, maybe all of my queries are merged, and then I'm getting OMN time overall. So you see, the problem is kind of the opposite, right? Here, so adding an edge was really cheap, but querying was not cheap at all. I had to spend linear time on it. Here, it's the opposite. Querying is really cheap. Adding an edge or merging two sets is actually very time consuming. I want something in the middle, right? I would like to spend just a tiny amount of time on querying and also a tiny amount of time on merging. Because I don't have any control over my input, I don't know what operations my input is asking me to do. In this case, I might have a lot of merges, and then that would be bad for me. In this case, I could have a lot of queries, and that would be bad for me. Okay. So here's one idea. Let's just optimize this part a little bit. So I'm saying, I'm looking at two different sets here, the set represented by RU and the set represented by RV. And then when I want to merge them, I'm going over all of my items. And basically for every item, I'm asking, are you in this set? If so, go to the other set, right? But I don't have to do this. I can just keep track of the set of items that are represented by U, right? And then I can just go over them and change them. So this would be a tiny difference, but let's do it. Let's say I have this. I'm going to call it S. And the size is max n as well. So the idea here is that Si is the set of elements represented by I. Okay. I'm just going to keep track of all the elements that are represented by every particular I. And again, here, when I'm saying that I is its own representative, I have to also say that in Si, add I. Okay. Now, what's happening here? So when I'm doing the merge, of course, I first do the query, that's fine. Then I'm finding the representative of each of these vertices, RU and RV. And then, instead of saying go over all of the vertices and see if they're represented by RU, I know exactly which vertices are represented by RU, all the vertices in S of RU. So I say for every X that is in S of RU, first of all, the representative of X becomes RV, and then X also should be pushed back into S of RV. Okay. So when I'm changing the representatives of some of the elements, I don't have to look at the other elements now. I'm just changing the representatives of these elements. And of course, at the end, if you want to be really nice, you can say clear S of RU, but I don't care about that. Honestly, it doesn't really matter. You can let it be. Okay. But this doesn't really help me, right? So yeah, in practice, I'm probably going over fewer elements. But in the worst case, I'm still going over all of my elements, right? So in the worst case, maybe I'm merging a really huge set, maybe the set of elements that are represented by RU, which are S of RU, maybe that set is huge. So imagine if U is in a connected component that has almost all the other vertices in it, right? If that's the case, I'm changing the representative of almost all of the vertices. So that's still going to take linear time. It's still theta n in the worst case. Okay. So here's the simple idea that would solve our problem here. Suppose I want to merge two sets. I basically have two choices here, right? So I can merge the set containing U into the set containing V, or I can merge the set containing V into the set containing U, right? So the other way of looking at this is that I have RU and RV, which are the representatives of U and V. And in the end, all of the vertices that were represented by both of them should be represented by only one of them. But I get to choose which one, right? So here, basically what I'm saying is that instead of going over every X that was in the same connected component as U and saying that now your representative is the representative of V, I can just say go over every X that was in the connected component of V and say that your representative is now the representative of U, right? This is symmetric. Both of them would work. But which one would I prefer? So the runtime of this for is basically proportional to the number of elements for whom I'm changing the representative. So I want to change the representative of as few elements as possible. So I want to merge the smaller set into the larger set. So that's the rule that I'm going to use. And this is basically all of this session. Always merge the smaller one into the larger one. Okay. So always merge the smaller set into the larger set. Okay. So great. What am I going to do here? Right now, I have these two. I have the set represented by RU and the set represented by RV. And I'm saying go over every X that is in the set represented by RV, which means every X that is in the same connected component as V, and set its representative to RU. And of course, when I set the representative, I have to update this S as well, because S of I is the set of elements represented by I. So I have to add X to S of RU. But I want to do this only if this is the smaller set, right? Now, you can write an if and do this twice, or you can just do this. You can say check if S of RV has a size that is bigger than S of RU, just swap them. Okay, so this makes sure that RV is the representative of the smaller set now. And then this one just merges the smaller set into the larger set. Okay. Now, again, this just seems like a heuristic. It seems like we didn't gain anything, because what am I doing? I'm just changing the representatives. And in the worst case, maybe both of my sets are really big. Imagine if I have two sets and each of them has half of all of my elements. So this would still take ON, right? So my merge is still ON and my query is still O1. But the thing that is interesting is what happens when I do a large number of merges. So remember, I have M operations here, and this M can also be huge. So of course, I can say that every merge in the worst case takes ON time. So if I do M operations, M merges in the worst case take OMN time. But I can do a better analysis. I can count the cost of a bunch of merges in a different way. Here's the thing. What is the main time-consuming component in a merge? It's this part, right? It's basically changing the representatives. So if I can just find the bound on how many times the representatives of some item changes, I have a bound on the overall runtime of all of my merge, right? So instead of just looking at one merge operation, I'm going to say, suppose you have given me many merge operations, and I'm just going to look at one of my items. I'm going to look at X. And I'm going to ask how many times does the representative of X change? Now, remember our golden rule. We always merge the smaller set into the larger set. So if I look at some element X, okay, so I have my element X, and initially it's represented by X itself. Now, let's say at some point, so the representative of X is initially X. Let's say at some point I change it, I update it to something else, X prime. What does this mean? It means that X was in a connected component that was merged with another connected component, but X was in the smaller one, right? So the size of the connected component containing X has at least doubled, right? And generally, I can say this several times. So let's say my representative changes from X, or let's call it X0 to X1, X2, X3, so on. So initially, I had a connected component or a set of size 1. The fact that I changed that representative to something else means that I merged this connected component with a bigger connected component, or at least a connected component of the same size. Because when they're equal, I'm doing it arbitrarily, right? So when my representative changes from X0 to X1, the size of the connected component containing X has at least doubled. But then I can say the same thing from X1 to X2, right? When I changed my representative from X1 to X2, it was because the set of all the items that were represented by X1 was merged with the set of all items that were represented by X2, and the set represented by X2 was the bigger one. So every time that my representative changes, the size of my set or the size of my connected component doubles, which means that as one item, I can change my representative at most log n times, right? Because the size of my set can be at most everything, all the n elements. So this means that if I just look at this line, the line that is changing the representative, over my entire program, this line is going to be run at most O n log n times, right? Because for every X, it's going to be run at most log n times. So overall, it's O n log n times. Now, it's pretty easy to check that everything else is just a constant times the number of times that you're changing the representatives. So this is also your overall runtime. So now, even though I have these things, if I do M merges, it doesn't take O and M, it actually takes O M plus N log N. Now, the N log N part is for the merges that are actually changing the representatives. And the M part is for the merges that are just doing queries and don't do anything else. Okay? So this is now much faster. And of course, if I have M operations overall, my runtime would also be M plus N log N because my query takes constant time. Okay. So as you see, a very small change, again, literally 2 lines of code, changes the runtime very dramatically. Now we're going to do something else. We're going to look at it again using the graph representation, but we're going to talk about how to choose this representative. So I'm just going to give you other algorithms that gain the same runtime. And then towards the end of this session, we will see an algorithm with a slightly better runtime. But basically, all of our algorithms are about how to choose the representatives. So this is an alternative algorithm. And the idea here is, instead of just thinking of representatives, let's say that I save each one of my connected components as a tree. Because if I have a connected component that is not a tree, that's a connected component that has too many edges. I can remove some of its edges. I can just keep a tree. I can keep like a spanning tree of it. And that's all the information that I need. Another way of looking at this is that here, when I was adding the edge from 1 to 5, I didn't need to add it. I could keep my connected component a tree. Okay, so this is the idea. Make sure every connected component is a tree. Okay. So just as before, I'm going to start with my vertices, each in their own connected component or their own set. So I have this 1, 2, 3, so on to n. And I'm going to save these trees also as like directed trees. So I'm going to know who the root is in every tree. So let's say I save every connected component as a rooted tree. And then basically the idea is that I'm going to use the root of this tree as the representative of my connected components. Okay. So 2 operations. I have query. When I do query ij, I'm basically asking are I and j in the same tree? So I can start from vertex I and I can keep walking up my tree until I get to the root. And then I can do the same thing from vertex j. And then I can ask, did I reach the same root or did I reach 2 different roots? Right? If I reach the same root, they were in the same connected components. So query ij would just be walk from I or j to the root. And then compare roots. Now, if I want to add an edge from I to j, or if I want to merge the sets containing I and j, again, I can do something similar. I can start at vertex I, and I can keep going to its parent until I get to the root. So I start from I keep going up until I get to the root. Let's call this R. Okay. And I do the same thing from vertex j. So I start from j, I keep going up until I reach a root. Now, if I reach the same root, well, they were already in the same set, so I don't need to merge anything. And this is basically also how my query works. But now let's say that they weren't in the same set. So I have this. I have R, and here, let's say, or maybe let me call this Ri, and let me call this one Rj. So I started from each of my vertices. I just went up my trees, and I reached 2 different roots. Now, when I want to merge them, I can simply make one of the roots the child of the other root. Right? So I can just say this Rj becomes the child of Ri. Or actually, I can move it around. So let me put it here. And then I add this new edge. So I just make Rj a child of Ri. Okay. So this is my merge operation. So basically, if you think about it, I really just have a root finding operation, right? So if I just have this operation of starting from a vertex and walking up until I get to the root of my tree, my query does this for both of these vertices, and then at the end just checks if they're the same root. My merge does it for both vertices, and at the end makes one of the roots a child of the other root. Okay? So this is the algorithm that we have using trees. And let me just copy the previous code. So I don't have these things anymore. I don't have representatives. I don't have the set S. I basically just have a parent for every node, because that's how I save trees. I just know who the parent of each node is. And I'm going to erase all of this, because I'm going to do my merge differently, and I'm going to do my query differently. So here's the thing. When I'm initializing it, everyone is in their own, let's say, tree, because every connected component is just one vertex. And now I can represent this by saying that the parent of I is just I. So I say the root is its own parent. You can also say that a node is root if it doesn't have a parent, or the parent is 0 or something. It doesn't really matter. You can do whichever you like. I prefer to say that the parent of I is I itself. Okay. Now, here's the operation that I need. I need to have a root operation, which basically takes a vertex U, starts from U, goes up the tree until it gets to the root and returns that root. Okay. Now you can write this recursively if you want. You can also just write it with a for loop or a while. I can just do this. I can say while U is not the same as the parent of U, U becomes parent of U, and then return U. So the step here is just going one step up the tree. U becomes its parent. I'm just going up. Okay, for how long am I going to do this? As long as I'm not the root. But how do I check that I'm the root? I'm the root if I'm the same as my parent. Okay. You can also write this recursively, of course. You can say, if U is equal to the parent of U, return U. Otherwise, return the root of parent of U. Right, that's also fine. Okay, now when I want to do query, when I want to say U and V, are you in the same connected component, same set or not? I just return whether root of U is equal to root of V. Okay, and when I want to merge, as I said before, I just take the two roots and I make one of them the child of the other one. Okay, now we can also write this one in one line of code. So I can do this. I can say the parent of root of U becomes root of V. Okay. Why does this work? Because basically I'm saying find the root of U and find the root of V as well, and make one of them the child of the other. Make root of U the child of root of V. It works even if they are in the same component, because if they're in the same component, then root of U and root of V are the same. But that's fine, because it's a root and it can be its own parent. That's why I was doing this thing here. Okay. If you don't want to do these things, you can just query and so on. So the normal way of writing this, if you're not doing things like me, is this. You just say root of U, let's compute that. Let's compute root of V. And then if they're the same, just don't do anything. Otherwise, make the parent of one of them, parent of RU, to be RV. Okay. Yeah, one line or 5 lines, your choice. Now, we have the same issue as before. What is our runtime here? Actually, this reminds me a little bit of the binary search trees as well. Look, so when I'm doing query, I'm doing 2 root operations. And then I'm not doing anything else. I'm just comparing them. So this is query is 2 root operations. Merge is also 2 root operations. So at least I've got to a point where my query and my merge are taking the same amount of time. But the question is, how much time is it taking? So how much time does it take to compute the root from one particular vertex? Well, in the worst case, this vertex is maybe a leaf in the lowest level of my tree, and then I have to take all the way up. So it's OH, where H is the height of the tree. Okay. So now I have that my query takes OH time, and my merge also takes OH time, because I'm starting somewhere in the tree and I'm just going up. In the worst case, I'm starting at the farthest point from the root, and that's like the height of the tree. Okay, so we are back to this situation that we want the heights of our trees to be small, right? Because if I have a small height, I will get a good runtime here. Let's say, for example, I want my height to be log n. Now, remember this golden rule. Always merge the smaller set into the larger set. I can do the same thing here. So when I have 2 trees and I want to merge them together, I have to take the root of one tree and make it a child of the root of the other one. Now, I can say I just keep track of the size of each tree. And I always merge the smaller tree into the larger tree, right? And if I do that, then I have an argument just like before that says that the height of my tree is at most log n. Because every time that I'm increasing the height of my tree, I'm doubling the size at least. Or again, another way of doing this is look at one vertex. Before we were looking at when the representative of this vertex changes, but now just think of when the root of the tree containing this vertex changes. Every time that the root changes, the size of this tree is doubling, right? So basically what this proves is that we always merge the smaller tree into the larger tree. Let's say merge the smaller tree into the larger tree. And basically, because of this, I know that my height is always in O of log n. Okay, so all of my operations are going to take log n time. So, but, well, how can I do that? Well, basically, I have to know the size of all these trees, right? So I'm just going to introduce something else. Let's say S, and basically SI is the number of descendants of vertex I. Okay, it's the number of descendants of I, including itself. So if I look at I and everything that is below it in its tree, how many vertices are there? That's what I'm saving in S of I. And well, here initially all of these sizes are 1, right? And when I'm merging, here when I'm saying that RU becomes a child of RV, that means that the size of the descendants of RV is going to increase by the size of the descendants of RU, right? But then, of course, we also had this rule that I always want to merge the smaller into the larger tree. So here I'm getting rid of RU. I'm merging RU into RV. So I say if the size of RU is larger than the size of RV, just swap them, so that I always know that RU is the root of the smaller tree. And I'm always merging the smaller tree into the larger tree. So this is now, of course, going to give me a runtime of OM log n. But here's the thing. What's our goal? Our goal is to keep the heights of these trees small, right? But what did I do here? I said that I always merge the smaller tree into the larger tree. Where did this idea come from? It came from this previous algorithm because we kind of magically knew that it will work, right? But let's forget this. Let's forget that we know the previous algorithm. And let's just imagine that the operations I have are merge and like finding root and so on. And I want to merge 2 particular trees. And what I really care about is the height of the resulting tree. Can I always just make the optimal choice? So let me just give you an example. Let's say I have this tree, and then I have this one. And I want to merge them. Okay. Now, you can say that, well, this one has 2 vertices. This one has 5 vertices. So I make this one a child of this one. Right? Fine. But what if this one actually had a ton of vertices? So imagine that it has, whatever, 1 million vertices. Okay. So now our algorithm says that, well, you have to make the smaller tree a child of the larger tree. So you have to basically take this tree and make its root the child of the root of the other tree. You have to do this, okay? And that's fine because we've already proven that our algorithm gives us a height of O log n in any case. But you can also see that this is not optimal, right? Because I don't really care about the number of nodes. I actually care about the height or the depth of the tree. So it actually makes sense to always merge the tree with the smaller height into the tree with the larger height. So in this case, it would make more sense if I take this one and make its root the root of everything. Okay. Now, why is that? Generally, let's say that I want to merge two trees and they have two different heights. Suppose we merge two trees, let's say T1 and T2. And let's say that they have heights H1 and H2. And let's say that I'm merging T1 into T2. So I'm making T1's root a child of T2's root. What is the height of the resulting tree? What is the resulting height? So here's the thing. Let's say this one had root R1 and this one had root R2. So I'm making R1 a child of R2, right? R2 already has all the children and descendants that it had before. So it has a bunch of things here. And we know that this part had a height of H2. R1 also has all the children and descendants that it had before. So we know that this part has a height of H1. So my total height is going to be the maximum of H1 plus 1 and H2. Right? And okay, so maybe I have to do this better. This H2 contains R2 as well. Right? So my final height is just the maximum of H1 plus 1 and H2. Now, why is this? Because if I had a node that was in the second tree in T2, its distance to the root did not change. If I had a node that was here, its distance to the root has increased by 1 because of this one edge. So my final height is just the maximum of H1 plus 1 and H2. But this is that if I want my final height to be as small as possible, I should always merge the tree with the smaller height into the tree with the larger height. So here's the thing. I have one way of merging that gives me height O log n. I have a different way of merging that is optimal. I know it's better than the previous way at least. So if I do this, my height will not be more than the same height that I would get with the previous one. So my height in this case will also be O log. So I said all of this just to say that instead of keeping track of the number of vertices, you could alternatively just keep track of the height. So DSU trees, I'm going to call this one DSU trees height. Okay, so instead of keeping track of that, I'm just going to have an H, and HI is the height of the subtree rooted at vertex I. Okay. Again, originally the heights are 0, so I would set HI to 0. Actually, I don't even need to write this. It would automatically put 0 anyway. And then whenever I'm merging, instead of saying that the size of RV increases by the size of RU, I just say the height of RV becomes the maximum of whatever it was, and the height of RU plus 1. Okay. And here again, instead of saying that I merge the root with the smallest size into the root with the larger size, I just use height. So the code changes by very little. Okay, hopefully this will compile. DSU trees. And yes. Okay, nice. Now again, this doesn't necessarily have a better runtime asymptotically speaking, but in practice, it's going to be a little bit faster. But let's just think about other ways that we can make it faster. So the whole point of using these trees instead of using our original system of representatives was that I don't need to change a lot of things, right? So when I was working with representatives, when I merged some set into another set, I had to change the representative for every member of that set. But when I'm working with trees and I want to merge two of them, I just have to change one pointer. I just have to take the root of one tree and say that you're now the child of the root of that other tree, right? So this is good for us because now I don't really care how many elements I have in my set. As long as I can find the root fast, if someone gives me the root, I can merge in O1, right? So this is the problem here. When I'm doing the merging, if I already knew the roots, everything after this is O1. So the only thing that I have to optimize is the height of my tree. I want my trees to have the smallest possible height. Okay. And this applies in both variants, no matter if you're merging based on height or you're merging based on size. So let's say we're merging based on size right now. We're always merging the smaller tree into the larger tree. But I also want to just have some heuristic to reduce the height. Okay. So this is the heuristic that I'm going to talk about here. It's called path compression. Now, the idea is very simple. I have to do the root operation over and over again, both in my query and also in my merge. And every time that I do a root operation, I'm basically finding some part of some tree. So let's say I'm starting at vertex I, and I keep going to its parent, so on, until I reach a root. I reach R, right? And of course, there is a lot of other things going on here as well. I don't know what else I have in my tree. When I'm doing one root operation, when I'm doing root I, all I'm seeing is vertex I and all of its ancestors until I reach the root. But here's the thing. I don't care about the structure of this tree. I only care about the root. So when I go through this path, I can also compress it by saying that all of you are now directly connected to the root. So I take this and I want to change it, and this is how I change it. I say vertex I know that your root is R, so now your parent is R. So you're going to be connected directly to R. Now this vertex, which was the previous parent of I, again, I know that it's in the same tree, and all I care about is which vertices are in this tree. So I can connect this one also directly to the root. And basically, I do the same thing for all of these vertices. I connect all of them directly to the root. How many were they? 1, 2, 3, 4, 5. And this is what I call path compression, for obvious reasons, because it's compressing this path. Right. And again, you can see that this helps, because finding a root is the only operation that we ever do, right? And now it means that once I found the root, I don't have to find the root again for these guys, unless I merge them. It's possible that I merge this node with some other node and then the root changes. But even then, they will be much closer to the root than they were before. So every one of the subsequent root operations is going to get faster because I did this path compression in this particular root operation. Okay. Let's do this. Let me take the version that was using size, and I'm going to call this one DSU3's path compression. Okay. So again, this is just using size, so I'm always merging the tree with the smallest number of vertices into the tree with the larger number of vertices. You can also do it with heights, but path compression gets a little bit harder with heights because you have to keep track of all the heights, right? So here's what I'm going to do here. I'm just going to say every time that I find the root of u. Now, previously, I wasn't saving anything. I was just starting at u and going up the tree. Now I want to save all the vertices that I'm seeing on the way so that I connect all of them directly to the root. Okay. So let's say I have a vector, and this is all the vertices that I'm seeing in the path from the vertex u to the root. Okay. And every time I'm just going to say in this path, put the current vertex and then go to the parent. So I just remember where I came from. And of course, at the end, u becomes the root. But just before returning u, just before returning the root, I'm going to go over everything in this path, and I'm going to say you are now directly connected to the root. So I'm going to say for every vertex v that is in this path, the parent of v is u. Okay, that's all the change that I'm going to make. Now, a fact that I cannot prove in 3711, but I'm going to give you a video for it, is that this actually reduces the runtime. So previously, if we did m operations, our total runtime would be this. It would be m plus n log n, right? Now, my total runtime would decrease to m plus n log star n. So the log becomes a log star. And for those of you who don't know what the log star is the number of times that you have to apply the log function until you get 1. It's going to be 0 if n is less than or equal to 1. Otherwise, it's 1 plus log star of log of n. So basically, if I have a number n, how many times should I take its log until this number becomes less than 1? To visualize this, log star of 1 is 1. Sorry, 0. Log star of 2 to the power of 1. Okay, so this is just going to be 1 plus log star of 1. So it's going to be 1. So log star of 2 is 1. Now, if I take log star of 2 to the power of 2, okay, that's 2. Log star of 2 to the power of 2 to the power of 2, that's 3, and so on. Okay, so another way of looking at this is that I have a tower of exponentials, and the log star of my number is the number of 2's in this tower of exponentials. So if I have the log star of 2 to the power of 2, so on, and this is k times, then that's k. So for any realistic number that you would ever find in a normal computer, the log star is at most 5 or 6, right? So for all practical purposes, this is like a linear time algorithm, but it's not a linear time algorithm theoretically, right? Because the limit as n tends to infinity of log star n is actually infinity.